Okay, welcome to our sixth video in which we look in more detail at the graph of y equals sine x and y equals cosine x, and we introduce the graph of y equals tan x. Well, what we saw in the last video was this. Let's just revise for a moment. The red graph is y equals sine x. We learned some of the x-intercepts. We have 0, we have pi, we have 2 pi. The period is 2 pi, or 360 degrees. Because as we go around the unit circle, everything repeats for the sine ratio after 2 pi of 360 degrees. And there's more we can say. The range is y between 1 and minus 1. That's because of the unit circle. And there's a new word we can learn. This distance here is called the amplitude. And that's 1. And the other graph is y equals cosine x. And if you look closely at it, it also has the same period, the same range, and the same amplitude. In fact, it's exactly the same shape. It's just in a different position. Remember, I said the values attained by cosine are the same as the values attained by sine, just in a different place. Let's look at that idea in a bit more detail. It's in a different place, and if you look closely, if I take this graph and translate it horizontally by a distance of pi over 2, I get to the sine graph. Now we can express that as as cosine x minus pi over 2 equals sine x, because we learned that this affects a horizontal translation by this vector. You can actually see that pretty easily if I draw over this in black. And then just imagine translating it across there. It goes on top of the sine graph. Okay. In fact, this is an identity right here. It's another identity. Let's look at it in a little bit more detail with our old friend, the unit circle. So here we have a point traveling around the unit circle. The red segment is giving the measure of the sine of the angle. I'm going to subtract 90 degrees from that angle to make another point. Now, this point here is 90 degrees less than the angle made by A. Okay, I've just subtracted 90 degrees. And the blue line is the cosine of that angle. So basically the red line is like sine x, and the blue line is cosine x minus 90 degrees, or pi over 2. Look at those lines. Wherever I go, they are exactly the same, both in size and sign, as in positive, negative. Those two triangles are congruent triangles. They're the same sides, the same angles. So here the unit circle confirms sine x is equal to cosine x minus pi over 2. Okay. Now, let's go back to the graphs. We can think about the graph of tan now. We haven't spoken about that. Now, before we look at the unit circle, and the unit circle tells us so many true things. This is a view that we had in a previous video. Do you remember that tan theta is sine theta over cosine theta? It's the gradient of this line. Okay. Now we're going to be considering this triangle as well today. Now it's a similar triangle because it has 90 degrees here and 90 degrees here, and it shares this angle. Now the gradient here is the same as the gradient in the other triangle. And when I make this dimension here, instead of cosine theta, I've gone all the way to the edge of the circle, so this is now 1. Then this dimension here must be tan theta. Think about it. The gradient of this line is tan theta because it's sine theta over cosine theta. And if I make this dimension 1, well, the ratio tan theta over 1 is obviously tan theta. It has the same gradient. Now what we're going to see in the unit circle, we've identified previously that the y coordinate is sine and the x coordinate is cosine. It turns out that this length here gives us the value of tan. Okay. In fact, if you look at it closely, it is a tangent to the circle. That's another way to think about it. So this measurement here gives us the value of tan. And we can see that here. So we're back in the unit circle. We've got sine is red, cosine is blue. And now when I add another construction here to show the gradient, this dimension here, this length, is tan. Now look here, the gradient is 0. How many degrees would it be to get gradient 1? 45, round about there. See that dimension there? It's pretty much 1. Okay, the gradient is 1. And then the gradient gets steeper and steeper, so this length gets steeper. And what happens at 90? It's not defined, it's vertical. In this quadrant, we've already seen tan is negative, so this is a length in the negative direction. And here, we've seen the gradient of this line is the same as the gradient in the first quadrant. It's positive, so this is a positive value. And in this quadrant, we have a negative gradient, so this is negative. So this tangent graph goes from being defined to not defined. It's not defined there, and it's not defined here. So let's plot that point. So this point, like we did before, the independent variable is the angle, the dependent variable is the tangent. And we can get an idea how that goes. Okay, and then if we trace the graph, the point, it gives us the shape of the tangent graph. which we can then make a little bit more permanent, like this. So it looks completely different to sine and cosine. So here's the graph of tan. Let's look at its features. We have a vertical asymptote here at x equals pi over 2. And we had another one at x equals 3 pi over 2. And so on. X equals 5 pi over 2. X equals 7 pi over 2. And we've got an x-intercept here at 0. We've got another one at pi. Think about it. The gradient of the segment when x is 0 or x is pi is 0. We've got 2 pi. We've got 3 pi. We've got 4 pi. Okay. Does this function have amplitude? No, because this goes up to infinity. And this goes down to negative infinity. Okay. But it does have period. What is the period? It's the smallest length of the repeating part. Well, if I take this part here, and just imagine copying and pasting that part, well, I get all these parts. It's easy to see that the period of tan is not 2 pi, it's pi. Okay, so that's our introduction to the graph of tan. Quite technical. Well done for listening. And in our next video, we will take those graphs and transform them and move them around, rather like this beautiful sculpture has been moved around and bent into different shapes.